Examples of empty sets in real life. So we've already talked about what empty sets are, sets that contain absolutely nothing. Now, on this slide, we're going to move beyond just the definition and really see how this idea of an empty set shows up in the real world. Just as a quick reminder, an empty set is a set with no elements inside it. It doesn't mean the set is useless or doesn't exist. It just means there's nothing currently in that set. And why is this important? Well, being able to identify empty sets isn't just a trick question. It demonstrates that you truly grasp this fundamental concept of set theory and how it can be applied to different situations. In the following slides, we'll walk through several examples, breaking down exactly why certain sets end up being empty. So, let's get started with our first example. Step 1. Understanding the core concept. So we've just started looking at how empty sets show up in real life, and we've established what an empty set is. Now, before we jump into specific examples, let's just quickly reinforce that core concept. This slide reminds us that a set is considered empty if, and only if, it doesn't contain any elements. Think of a set as a container, and an empty set is simply a container with nothing inside. Now, a common misunderstanding is thinking an empty set is the same as nothing. That's not quite right. It's not that the set doesn't exist. It's that there are no items that meet the criteria to be included as members of that set. So we might define a set with certain rules, but if no things actually fit those rules, then the set is empty. We'll see this in action with the examples coming up, but it's important to understand this distinction now. We'll be using the symbol, which looks like a circle with a line through it, or just curly braces with nothing inside, to represent an empty set. We'll see that notation a lot as we work through these examples, and in the next slides, we'll start applying this to some scenarios you might encounter in everyday life. Step 2. Example 1 months with 32 days. So let's move on to our first real-life example of an empty set. As we discussed in the previous slides, remember that an empty set is simply a set with absolutely no elements inside it. Now, to help solidify this concept, we're going to look at some scenarios where empty sets naturally occur. Here, we're going to define a set called A. We're saying that set A consists of all the months in a year that have 32 days. Let me write that out formally. We represent this as A equals the set of months with 32 days. Now, let's analyze this. Think about the calendar year. How many days does each month have? January has 31, February has 28 or 29, March has 31, and so on. If you go through all 12 months, you'll quickly realize something. There isn't a single month that has 32 days, is there? That's the key point. Because no month satisfies the condition of having 32 days, the set A contains no elements at all. Therefore, we can confidently say that set A is an empty set. We represent an empty set using a special symbol. It looks like a circle with a line through it, and we call it the empty set symbol. Or, we can simply represent it with empty curly braces. So we write A equals the empty set, or A equals an empty set enclosed in curly braces. This demonstrates how an empty set can arise from a perfectly valid definition, but where no actual elements meet the specified criteria. In the next examples, we'll continue to explore similar scenarios, building on this understanding. Step 3, Example 2, Even prime numbers greater than 2. Let's move on to our next example of an empty set. As we've been doing, this will help solidify our understanding of how these sets appear in real-world scenarios. This slide introduces a set we'll call B. We are defining set B as the set of all even prime numbers that are greater than 2. Now let's break that down. We write this mathematically as B equals the set of even prime numbers such that the number is greater than 2. Remember, the vertical bar means such that it introduces a condition. Let's analyze what makes up the elements of this set. First, recall what a prime number is. A prime number is a whole number greater than 1, and it can only be divided evenly by 1 and itself. So, for example, 7 is prime because only 1 and 7 divide into it. Next, an even number is any whole number that is divisible by 2. Think of 4, 6, 8, and so on. Therefore, since there are absolutely no numbers that satisfy both conditions, being even, prime, and greater than 2, the set B contains no elements. This means set B is an empty set. We represent this by writing B equals the empty set, or simply B equals an empty set using curly braces. Remember, the empty set is denoted by either a symbol that looks like a capital O with a slash through it, or just empty curly braces. Now here's the key point. The only even prime number is 2. Why? Because 2 is divisible by 1 and itself, fitting the definition of a prime number. However, any even number greater than 2, like 4, 6, 8, and so on, is divisible by 1, 2, and itself. That means it has more than 2 divisors, and therefore, it's not a prime number. This is another example of how we can define a set with specific rules, and if no numbers fit those rules, we end up with an empty set. We'll look at a couple more examples, and then we'll recap the key takeaways and common mistakes to watch out for. Step 4. Example 3 students in a class who are also teachers. Let's move on to our next example of an empty set. As we've been doing, this will help solidify your understanding of how these sets appear in real life. Now, let's consider a typical middle school class. We're going to define a set, and we'll call it C. Set C will consist of students in that class who are also teachers in the same school. So mathematically, we write this as C equals the set of all students such that the student is also a teacher. Remember that, such that just means with the condition that. Now let's analyze what elements could possibly be in this set. Think about the roles of students and teachers. Generally, students are the ones receiving instruction, being taught by someone, and teachers are the ones providing that instruction. It's quite unusual, wouldn't you agree, for someone to be simultaneously a student, actively learning in a class, and a teacher, actively teaching in that same school, especially within the same class. So, assuming, and this is a reasonable assumption in most middle school scenarios, that no students are also teachers in that class, then the set C contains absolutely no elements. Therefore, the set C is an empty set. We represent this by writing C equals the empty set, or simply C equals an empty set enclosed in curly braces. Both notations, the empty set symbol and the empty curly braces, mean exactly the same thing, a set with nothing inside. Keep this in mind as we move forward. Identifying these conditions where no elements can satisfy the set's definition is key to recognizing empty sets. And remember, on the next slide, we'll cover some common mistakes students make when dealing with these concepts, so pay close attention. Step 5. Example 4 negative odd numbers that are also positive. Let's move on to our fourth example, and this one really highlights how carefully we need to think about the conditions defining a set. We're going to define a set called D. We're saying that D is the set of all numbers that are both negative and odd and also positive. Now, let's write that out formally. We have D equals the set of all numbers, such that the number is negative, odd, and positive. Remember, the vertical bar means such that it introduces the condition that defines what elements belong in the set. Let's analyze this. Think about what it means for a number to be negative versus positive. A negative number is less than 0, and a positive number is greater than 0. Can a single number be both less than 0 and greater than 0 at the same time? No, it can't. These properties are mutually exclusive. They can't both be true for the same number. Therefore, because no number can simultaneously satisfy all three conditions, being negative, odd, and positive, the set D contains absolutely no elements. This means D is an empty set. We represent this by writing D equals the empty set, which we denote as either the empty symbol or a set with nothing inside the curly braces. So, D equals the empty set, or D equals an empty set with curly braces. This example is important because it shows that even seemingly simple conditions can lead to an empty set if those conditions are contradictory. Keep this in mind as we move forward, because being able to identify these empty sets is a key skill in set theory. And in the next slide, we'll summarize the key takeaways from all these examples. Key takeaways. Let's recap what we've learned about empty sets with these key takeaways. Firstly, remember that empty sets don't just happen randomly. They arise specifically when we create a set by listing conditions or rules that absolutely nothing can meet. So, if you define a set with requirements that are impossible to fulfill, you've automatically created an empty set. Think back to our examples, the months with 32 days, or numbers that are both negative and positive. The conditions themselves made it impossible for any element to be included. Secondly, identifying these empty sets isn't about luck, it's about careful thinking. You need to really analyze the defining characteristics, the rules of the set. Ask yourself, is there anything that could possibly satisfy all of these conditions simultaneously? If the answer is no, then you're dealing with an empty set. We practiced this with the even prime numbers greater than 2 and the student-teacher example, really breaking down what each term meant. Finally, and this is important for notation, we represent an empty set using either a special symbol, which looks like a circle with a line through it. Mathematicians often call this the null set, or simply by using empty curly braces. So, both the symbol and empty braces, which look like two vertical lines right next to each other, signify a set with absolutely nothing inside. Now, before we move on to common mistakes, remember that understanding why a set is empty is just as important as recognizing it. This shows you truly grasp the concept of set theory and its applications. Common mistakes. Remember, an empty set, which we represent as either the empty symbol or curly braces with nothing inside, means there is absolutely nothing within the set. It's not the same as a set that contains the number 0. The set containing 0, written as a curly brace with 0 inside, does have one element, the number 0. So, the empty set and the set containing 0 are completely different things. Don't fall into the trap of thinking they're interchangeable. This is about being a careful reader. When we define a set, we often do so by stating certain conditions that elements must meet to be included. For example, remember the set of months with 32 days? To determine if a set is empty, you must carefully read all the conditions and make sure no element can possibly satisfy all of them simultaneously. If even one condition isn't met, that element isn't in the set. This is a conceptual misunderstanding. It's perfectly okay and mathematically valid to define a set that turns out to be empty. Just because we define a set doesn't mean it has to contain something. As we've seen with our examples, sometimes the conditions we set up simply don't apply to anything in the universe of things we're considering. Let's move on to the final slide, which highlights some common mistakes students make when dealing with empty sets. This is really important, so pay close attention. So, keep these common mistakes in mind as you practice identifying empty sets. It's all about precision in your definitions and careful consideration of the conditions you're setting. That concludes our discussion on empty sets and their real-world examples. Do you have any questions about anything we've covered?